So now we're going to talk about Newton's law of cooling and warming, and we said that the differential equation for Newton's law of cooling and warming was d capital T over d lowercase t equals k times the difference between T minus Tm. Remember that capital T is the temperature of the item, Tm is the temperature of the surrounding medium, and then that lowercase t is with respect to time. So we're saying that that change in temperature of the item with respect to time is directly proportional to the difference between the temperature of the item and the temperature of the surrounding medium. So we can take that differential equation and we can solve it by separating the variables. So we can multiply both sides by dt, which will get us here, and then we can divide by T minus Tm. Now keep in mind that Tm is actually a constant value. We'll know that temperature of the medium based on whatever the problem tells us it is, or what it we may end up having to find that in some cases. We may not know that, but we'll have enough information to do that. But that Tm is a constant value. It's the temperature of the surrounding medium for the item that we're putting into that medium. So if we integrate both sides, we're going to get the ln of T minus Tm is equal to kt plus c. We're going to rewrite as an exponential, so it's going to be e to the kt plus c, but we could rewrite that as c1 e to the kt is equal to capital T minus Tm. And I'm going to solve this guy for t. So there's our differential equation solved. I'm going to approach these two problems a little bit differently. They're going to use that same differential equation. So we already know what it is. We've solved it. Now we can just do our substitutions and figure out what the question is asking for. So let's look at 14. We're going to use that model that we just derived. To solve this. It says a thermometer is taken from an inside room to the outside where the air temperature is 5 degrees. So we know the temperature of the medium is 5 degrees. They say after 1 minute, the thermometer reads 55 degrees. And after 5 minutes, the temperature of that thermometer is 30 degrees. So we can see that that temperature is approaching that 5 degree, which is the temperature of the medium. We're asking, what was the initial temperature? So we're saying at time 0, what was the temperature of that item? So we know the temperature of the medium is 5 degrees. We have two constants we have to find, this C1 and this K. And we have enough information to do that. So we're going to make some substitutions in here. We're going to substitute in that first set of values. So that temperature is going to be 55 degrees after 1 minute. And then we're going to substitute in that second piece of information, where the temperature is 30 degrees after 5 minutes. So that 5 is going in for this lowercase t. So we have a system of equations. They are nonlinear equations, so we cannot just plug this into a calculator. But here's what we know. We know is 50 is going to be equal to C1 e to the k. I'm going to solve this for e to the k, similar to what we did in another video. And then I'm going to make that substitution in here. So I'm going to go ahead and move that 5 over. They give me 25 on the left. So that's equal to C1 times e to the k to the 5th. Our e to the k is 50 over C1. So now we have 25 is equal to C1 times 50 to the 5th over C1 to the 5th. So 25 is equal to C1 times 50 to the 5th. And if I take this C1 and I divide by C to the 5th, I'm going to end up with a C1 to the negative 4th right there. Which is the same thing as writing this as 50 to the 5th over C1 to the 4th. So we're going to have C1 to the 4th times 25 is equal to 50 to the 5th. C1 to the 4th is equal to 50 to the 5th over 25. And if I take everything to the 1/4 power, I get that guy. So that's my exact value. Just if you're curious about the decimal approximation, is 59.4604. I would still use your store feature to store that value. But now that we know C1, well, in this case, we really don't need to know the K because we want to know what's happening at time 0. So here's our model. We have T equals the temperature of the medium, which is 5 degrees, plus our C1, which is this nice number, 50 to the 5th over 25 to the 1/4, times e to the k times lowercase t. We want to know what happens when t is 0. So you can see why we won't need that k value. We could find it. We could find the k value just by plugging that C1 in here and taking the ln of both sides. So this is going to be 5 plus this number, which is about 59.4604 times e to the 0, which is 1. So that temperature is about 64.5 degrees. I'm just going to round this to 2 decimal places. So the initial temperature of that thermometer was about 64 degrees. Now, if we wanted to know K, like I said, we could plug in here. So we're going to have 50 divided by our C1. And then if we take the ln of both sides, that would give us our K value. And just for fun, I got approximately negative 0.1733. If you're rounding things, you need to be careful. If we're rounding this final answer to 2 decimal places, ideally you want to go at least 4 out for everything else, so you can get the final answer to be correct to about 2. But if you want to know K, that's about what it is. Notice that K value is negative. It's always going to be negative with Newton's law of cooling. So let's do the next one. Let's look at 15. So in this problem, we have a small metal bar. The initial temperature of the bar was 20 degrees. So that's telling us what's happening at time 0 for the temperature of the bar. It's dropped into a container of boiling water, so we know the temperature of the medium. We want to know how long is it going to take for the bar to reach 90 degrees if it's known that the temperature increases 2 degrees in 1 second. And then how long is it going to take for the bar to reach 98 degrees Celsius? So let's look at this problem. So if we write down what we know, we've already solved the model. So we know that T equals the temperature of the medium plus C1 e to the KT. We've got to figure out what this and this is going to be. We know what the temperature of the medium is. It's boiling water. This is in Celsius. So we know the temperature is going to be 100 degrees Celsius. We know that in the beginning at time 0, the temperature of the thermometer was initially 20 degrees Celsius. We want to know the temperature, we want to know how long it's going to take for the temperature to reach 90 degrees Celsius. And then we're going to do the same thing for 98 degrees Celsius. But we need the model to work off of. We also know one other piece of information, that it takes 1 second to increase 2 degrees. So that gives us some more information that we can use. We know in the beginning that temperature was 20 degrees. We know after 1 second of that thermometer being dropped in this water, the temperature has increased 2 degrees, which is 22 degrees Celsius. So that gives us 2 initial conditions, so we can solve for that C1 and that K value. So let's start doing that. Let's make some substitutions here. So I'm going to start with in the beginning. In the beginning, the temperature was 20 degrees. That's at time 0. Our temperature of the medium is 100. So we have negative 80 is equal to C1. Okay, notice that that is the difference between the temperature of the medium and the temperature of the item initially. And that's what that C1 is going to always represent there. So here is what we have so far. Our model, T is equal to 100 minus 80 e to the KT. So now let's use that second piece of information, where 1 second later we have 22 degrees. So we have negative 78 is equal to negative 80 e to the k. So 78 over 80 equals e to the k. Take the ln of both sides. This guy does reduce to 39 over 40. And that's going to be our k value. So now we have a model that we can use. So we have T is equal to 100 minus 80 e to the ln of 39 over 40 times T. Now you do have to be careful here. A common mistake, and I'm going to write this in a different color. A common mistake is that people like to say e to the ln of 39 over 40 times t is the same thing as just 39 over 40t, and that is not the case. E to the ln of 39 over 40 times t is the same thing as e to the t times ln. I'm just changing that order. And this guy's actually an exponent on this. So this is really e to the ln of 39 over 40 raised to the t power. And now you can use that inverse property that says e's and ln's cancel each other, and you get 39 over 40 raised to the t power. Okay, notice that this is completely different than the mistake of saying that's equal to 39 over 40 times t. That t is actually an exponent on that number. So be careful if you're wanting to reduce those, and don't make that mistake. I'm going to leave everything in exponential notation as is. So we want to know, what is the temperature at 90 degrees? Excuse me, how long is it going to take for the temperature to reach 90 degrees? So I'm going to have 90 equals 100 minus 80 e to the ln of 39 over 40 times t. So I have negative 10 is equal to negative 80 e to the ln of 39 over 40 times t. So I'm going to have 1/8 is equal to e to that stuff. And now if I take the ln of both sides, this ln and this e will reduce. And that's going to leave me with the ln of 39 over 40 times t, because it's going to leave me with all that exponent, and all this is the exponent. So t is going to be equal to the ln of 1/8 divided by the ln of 39 over 40. And that's going to be approximately 82.13 seconds. And we could do something similar. They asked us to find how long is it going to take to reach 98 degrees. So what's the time to reach 98? So we're going to have 98 here equals 100 minus 80 e to the ln of 39 over 40 times t. So now we're going to have negative 2 here. Divide by negative 80, that's going to give me a 1 over 40. Take the ln of both sides. That's going to leave me with just the exponent on the right. So t is equal to the ln of 1 over 40 divided by the ln of 39 over 40. And that is about 145.7 seconds. So there's our final answer.